Hello and welcome. Today, we're going on an adventure. We're going to follow the incredible journey of a single raindrop, from the moment it's born high up in the sky, all the way through its wild path across the land, and finally out to the ocean. So let's dive right in. So let me ask you something. Where does a river actually start? You probably picture a little spring bubbling up from the ground somewhere, right? Well, the real story is so much bigger and way more connected than that. A river doesn't just start at one single point. It starts across an entire landscape, and that's exactly what we're going to unpack. To really understand this journey, we first need to get to know the stage where this whole drama plays out. We're talking about the river's catchment area, or what's also known as a drainage basin. Okay, the easiest way to think of a drainage basin is like a giant funnel, or maybe a massive bowl. Any rain or snow that falls inside the rim of that bowl is going to eventually find its way down to the same single exit point, the river. It's a living, breathing system with inputs, like rain coming in, a bunch of complex flows, which we'll get to, and finally outputs, where the water leaves. So let's start with that first part, the input. Where does our little raindrop even come from? Well, its story begins way up in the atmosphere, and it all hinges on a critical trigger point. You see, the air around us is holding water all the time as an invisible vapor, but it has a limit, and that limit depends on the temperature. The dew point is that magic temperature where the air is completely full. It's hit 100% relative humidity, and it literally cannot hold one more drop of water vapor. So what happens then? Well, it's a beautiful four-step process. First, warm, moist air near the ground starts to rise, and as it goes up, it expands and cools down. Second, it keeps cooling until it hits that dew point. At that exact moment, the air has to let go of its extra water vapor. That vapor then condenses around tiny little dust particles in the air, forming clouds. And finally, when those tiny droplets in the clouds clump together and get heavy enough, gravity wins. They fall as precipitation. And boom, a raindrop is born. And just like that, our raindrop has landed. Now, this is where its journey gets really interesting. It faces a whole series of obstacles and pathways on its trip to the river. Before it even touches the ground, our raindrop might get snagged by the leaf of a tree or a blade of grass. This is called interception. All the plant life basically acts like a giant, leafy umbrella, catching the rain and slowing down its race to the ground. In fact, some of this water might just evaporate right off the leaf and go back into the atmosphere without ever touching the soil at all. Okay, but for the water that does make it past the leaves and hits the ground, it now faces a critical fork in the road. It's a choose-your-own-adventure moment. Does it soak into the soil, or does it flow over the surface? The path it takes depends entirely on the ground it lands on. Now, this all comes down to something called infiltration capacity, which is really just a fancy way of saying how thirsty the soil is. On the left, imagine a light rain on dry ground. The soil can easily drink that water up, and it slowly infiltrates or soaks in. But on the right, picture a heavy downpour on hard, compacted ground. The rain is coming down way too fast for the soil to absorb it, so that water has no choice but to run off right over the top. And that journey is much, much faster. And here's where it gets really serious. What happens when the soil is completely full? You know, like a sponge that is totally saturated and can't hold another drop? At that point, infiltration just stops. Period. Every single new raindrop that falls is forced to run straight over the surface. This is called saturated overland flow, and it is a huge reason why floods can happen so fast during long periods of heavy rain. All right, so let's go back to the water that successfully infiltrated the soil. It doesn't just sit there. Some of it starts moving sideways, taking a journey through the upper layers of the soil, heading slowly but surely towards the river. We call this path through flow. But some of that water goes even deeper. It percolates, and that just means it trickles straight down, moving from the soil deep into the cracks and pores of the rock far below. This is a much, much longer and slower journey into the earth. Once that water makes its way down into these deep rock layers, it becomes part of this huge hidden reservoir called groundwater. Now, this water moves incredibly slowly. We're talking years, even decades, just to travel a short distance. But this groundwater flow is absolutely crucial. It's what feeds a constant, steady supply of water into our rivers, keeping them flowing even when it hasn't rained for weeks. So let's just quickly sum this up. You can think of these as three different travel speeds. You've got surface runoff, which is the sprinter, just racing across the land. Then there's through flow, which is kind of like the jogger, moving at a steady but slower pace through the soil. And finally, you have groundwater flow. That's the marathon runner, taking the super slow and steady path deep down in the rock. So our raindrop has traveled over, through, and under the ground. But how does water actually get out of the drainage basin? Well, there are two main escape routes. The first escape route is basically an invisible one. Water can evaporate from surfaces like lakes or wet soil. At the same time, plants are pulling water up from their roots and releasing it as vapor from their leaves in a process called transpiration. We lump these two together and call it evapotranspiration. It's the whole system breathing water back out into the atmosphere. And then there's the main exit, the river itself. All that water, from the fast surface runoff, the slower through flow, and the super slow groundwater, it all eventually finds its way into the river channel. The river then acts like a highway, collecting all those raindrops and carrying them out of the basin and back home to the ocean, completing the cycle. But here's the thing. This elegant natural journey is very rarely left untouched. Human activity can radically alter the path our raindrop takes, and it puts the entire system under a lot of pressure. And this right here shows you everything you need to know. On the left, in a natural forest, you have tons of interception by trees and high infiltration into the soil. That means runoff is low and slow, and the flood risk is much lower. Now look at the column on the right, a city. We've replaced spongy soil with hard, impermeable surfaces like concrete and asphalt. Interception and infiltration, they drop to almost zero. And the result? Surface runoff becomes incredibly high and dangerously fast, which massively increases the risk of urban flooding. And this really gets to the heart of the matter. A drainage basin is a deeply connected system. Paving over a field for a new parking lot might seem like a small change, but what you're really doing is removing a piece of that natural sponge. You're forcing more water into drains faster, which can overwhelm rivers miles downstream. Every single change has a ripple effect. So next time it rains, I want you to look outside. Don't just see rain. Look at the grass, look at the pavement, the drains, the trees. Think about the incredible, complex journey that every single one of those raindrops is taking, and ask yourself, how has the world we've built changed that ancient path? And what does that mean for the rivers that flow right through our lives?